How to apply KVL and KCL to a series in RLC circuits. So, first, let me give you a small details about RLC. So, what is RLC? RLC stands for resistance, inductance, and capacitive. So, as we have seen so far, when coupled to a sinusoidal alternating voltage, the three fundamentals, passive components of resistance, inductance, and capacitive, have quite distinct phase connections to one another. But by joining these components in a series with a voltage supply, we can create a series RLC circuits. So let's go back on how to apply KVL and KCL to a series RLC circuits. So in this, we have to, for example, we have DC voltage. By using this on how to apply KVL and KCL, we will use DC voltage. So for example, we consider a series RLC circuit with one voltage source, Vs. So by KVL, we write Vs equals VR plus VL plus Vc equals Ri plus L di all over dt plus 1 all over E. The integrations of t over point infinity numbers I, multiplication of R dt. So next, consider a parallel RLC circuit with one source. Is by KCL, we write Is plus IL plus IC equals V all over R plus 1 all over L, the integration of t over negative infinity numbers V multiplication of t dr plus c dv all over dt. So whatever that is, whatever that is how KVL and KCL operate in an RLC circuits, or the extensions, variations such as a resistor in series with a parallel LC should be obvious. So when the source is DC, however, the voltages and currents in the circuits are constant over time. So as there is no parallel voltage in a parallel case, there is also no current via the resistor. So the KCL equation is no longer true. Now, if you have a switch and a DC source, there are actually two circuits to solve and a transient that connects the two DC solutions. While drawing a circuit diagram, you must indicate the circuit's current flow direction, identify its constituent parts, and determine any unknowns. So you can do this by using the equation derived from KVL and KCL. So I hope it explained well on applying KVL and KCL to a series RLC circuits.